Hello, so welcome to this lesson on how to solve system of ODEs. Okay, so in this system of ODEs, the eigenvalues are distinct. Okay, so that one too, like I said, in the other lesson, I said that I will show you how to do such problems. Okay, so if you've not subscribed to my channel, kindly subscribe for more videos and also support the channel as well. Okay, now we said that to solve such a problem like this, you need to what we call the coefficient matrix, which is equal to, now since we have three equations, you have to get 3 by 3 matrix, and then it's just the coefficients, the entries are just the coefficients of the variables in each equation. So in the first equation, the coefficient, this equation here, okay, the coefficient of x there is 0. Okay, so you write 0. For that of y is 1, z is 0, and for the coefficient of variables in the second equation is also given as what? For x is also 0, for y is 0, for z is 1. So with the second equation, the coefficient there, let me write it well. The coefficient here for x is -5, for y is 5, and for z is 1. Okay, so the eigenvalues and eigenvectors of this matrix will actually solve the system of ODE given here. Okay, alright, so let's go ahead and find the eigenvalues and eigenvectors of this. As usual, sorry, I'm very sorry for what just happened. Okay, so as usual, as you know, what you do is, first of all, you find a minus lambda I. Okay, we will need this later, but I'm just writing it here, and it's equal to, looking at the way this matrix is, this is very simple: minus lambda 1 0 0 negative lambda 1, and -5 5 1 minus lambda. Okay, like that. This is what you have. Now I said that in the previous lesson I gave a formula for a 2 by 2. That one was squared. So for the characteristic polynomial governing this is p of y, or sorry, p of lambda is given by lambda cube, okay, minus trace of a lambda squared, okay, plus pm of a lambda minus determinant of a. Okay, kindly bear with me, and I hope you can see what I've written here. Okay, where the trace of a is just the sum of the diagonal elements, so the sum of these elements, and 0 plus 0 plus 1 is what? 1, and principal minus of a, that's the meaning of the pm. It's just that the principal minus the sum of all the principal minus of a, and this is how you find that. You stand on this first entry here, okay, and you cancel the elements here, you cancel the elements here, and you find the determinant of the rest of the elements, and that will be 0 times 1, which is 0, minus 5 times 1, which is minus 5. Okay, so minus 5. Let me write it well. Okay, so you get minus 5 for the first one. Okay, plus, then you come and stand on the second diagonal. So you stand on the diagonal elements, only the diagonal elements. So you stand on these elements, you cancel the elements here, you cancel the elements here. Now the rest is this 0 and 1, and this -5 and that. So 0 times 1 is 0, minus 5 times -5 times 0, which is 0. So at the end we get 0 for the second pm, or principal minor. Okay, so you get 0, then plus, you stand on this one, so you are just standing on the diagonal elements, you cancel here, you cancel here, you find the determinant of the remaining here, and that is also 0. Okay, that is also 0, and which is equal to -5. Okay, and then if you use your calculator, if you know how to use the calculator for the determinant of a matrix, I will leave the link to that video on the video description, or either in the comments as well, so just check it out and find it. The determinant of a is also given by 5. It's given as 5. Okay, is it -5? Yeah, -5 rather. Okay, so that is it for your matrix. And then if you want to find my polynomial, is simply this is equal to p of lambda is not p of lambda cube, is equal to lambda cube minus trace of lambda, which is 1 squared, plus pm is -5, so -5 lambda minus -5. -5 is the determinant, so minus it becomes plus 5. And now this becomes my characteristic polynomial governing this matrix. Okay, so quickly I'll go ahead and find the solution to that, the zeros of that, and that will be my eigenvalues. Okay, this is equal to lambda cube, okay, lambda cube minus lambda squared minus 5 lambda plus 5. Okay, so I equate this to 0 and solve for it. So lambda cube minus lambda squared minus 5 lambda plus 5 equals 0. Now if you use the calculator to find the zeros of this, you could find out that lambda 1 is equal to 2.236. is in decimal, but I approximated it to 3 decimal place. So lambda 2 is also equal to negative 2.23, okay, 236, and lambda 3 is equal to -1. Sorry, it's supposed to be +1 rather. Okay, so these are the solutions to this. Now I want to find the eigenvectors of these, and it's very tedious, but then let's go ahead. So we know the eigenvalues to be these. So what you do is, first of all, with the first eigenvector, you just find, we said that lambda, or a minus lambda I, and this I is a 3 by 3 matrix. Okay, is a identity matrix for a 3 by 3 matrix, and it's equal to, a was given as 0 something, so it was negative lambda, and I hope you remember that 1 0 0 negative lambda 1 -5 5 1 minus lambda. So we are coming to put all the eigenvalues in here individually. Okay, so when lambda equals, for lambda, let me put it here, for lambda 1 equals 2.236. okay, a minus lambda will be equal to what? A minus lambda I, where our lambda here is 2.236. And so here this will give us -2.236 1 0, then 0 -2.236. okay, then we have 1 here at -5 5. okay, I hope you can see what I'm writing. Let me raise and write them all. Okay, so with the first column, these are okay. Now with the second column, we will have 1 -2.2, okay, 236, and we'll have 5. The last column will have 0 1 -1.236. okay, so this will be it. And now if we let our v1 be equal to let's say m1 m2 m3. okay, so we said that in our last discussion we said that to find the eigenvector of a matrix is just a minus, okay, lambda I times your eigenvector, which is v1, should be equal to 0. okay, but before, if you can reduce the a minus lambda I, the matrix that we had, if you can reduce that for simplification purposes, or for simplification, then that will be easier. So let's go ahead and reduce this matrix. So the matrix we are about reducing is -2.236, then 1, or let me write it column wise, 0 5, okay, it's -5 rather, okay, then 1 -2.236, then 5 0 1 -1.236. 2.236. Okay, now with this matrix, what you can do is to solve this. First of all, let's find the multiplier, which is negative 2.236 divided by negative 5. Okay, and this will give me positive how do you call it, 0.4472. okay, this is what you get. Now we said that, and you want to transform this, what you have to do is you write your first row, which is row 1. The reason why we are doing this is, first of all, let me clear this. With the second row, the entry below it is 0, so we are okay. So we want to find a multiplier that can change this 1 to 0. Okay, and that is negative 2.236 over negative 5, and we had this as a multiplier. So we said that you transform row 1, row 3, the last row, we want to transform this row. So row 3 will be row 1, then whatever sign that is in front of this multiplier, you change it. Okay, here the sign is what, or you negate it. Here the sign is positive, so you do minus 0.4472 row 3 should give me a different thing. Okay, and with that, let me write it here. After everything, we know that the first row will be maintained 2.236. okay, 236, like that's 6. Then with the first column we have 0, and here will also be 0. If you check with your calculator, and you see 2.236. okay, like that, and this will be negative 1.236. okay, here will be 0, here will be 1, here will be 0.553. okay, you can write it, but I'll write it in the next page. So it's 0.553. You get a new matrix to be negative 2 point, let me change it to the marker so that we'll be able to move fast. Okay, alright, so we have negative 2.236. okay, and we have 1 here, we have 0, we have 0, 0 as well. Okay, and we have negative 2.236. okay, we have negative 1.236. you have 1 here, you have negative, or you have, is it positive, 0.553. all these transformations were being done. Okay, know that this 0 is here, this 0 here is here. Okay, so let me put it that way. All these transformations were being done through the multiplier, by the multiplier. Let me put it that way. Whoa, let me write it back. Okay, let me put it here. So I have 0 here, I have 1 here. Okay, so this is my reduced matrix. Now if I want to continue, then I have to make sure that the down part of the second row is also 0. Okay, the down part is also 0. So the multiplier here this time will be, let me use the other pen, and the multiplier will be, let's say M2. The first one was M1. M2 will be you have how do I call it, negative 2.236 divided by negative 1.236, and this will give me, is it 559 over 309. Okay, so what you do is, this is your multiplier. So what you do is row 2 minus, so since this is a positive, you negate it. 559 over 309 row 3 should give me a new row 3. Okay, so the other one, you could have said that this row 3 should give us a new row 3. Okay, here, like that. When you do that, what you get is, you get a new matrix of this form. Okay, reduced to negative 2.2236. okay, 1 0, and 0 here, negative 2.236, then 1, and we'll have something like 0 here, 0, and 0. Here, this entry is not approximately 0. I approximated everything to three decimal places. So the decimal you get 0.0000 something. It's negative 0.000 something. When you approximate it to three decimal places like we are doing, is 0. Okay. So it means that this is my a minus lambda I, where this lambda is what lambda 1, which is 2.23, whatever that you had. Okay, so like this, you said that a minus lambda I times our v1 should be equal to 0, and v1 we said m1 m2 and the rest. Okay, so you have negative 2.236, okay, 1 0, you have 0 0, negative 2.236, you have 1. Okay, let me write this here. 0 is here. Okay, 0 0 times m1 m2 m3 should give us the 0 vector, which is 0 0 0. Okay, so now if you continue, you get negative 2 point from the second row 236 m2 plus m3 is equal to 0. On the first row we have negative 2.236 m1 plus m2 is equal to 0 as well. So from this one, it means m2, if I make m2 the subject, is equal to 250 over 559 m3, right? Okay, and with this one, this implies that with the second equation, m1 is also equal to 250 over 559 m2. So here, since we don't have exact solution for it, means that we have infinitely many solutions. If you remember, we said that if one of the rows vanishes, that means we have infinitely many solutions. So what you do is you choose for one of them. You see, all of them are depending on m3, okay, because m2 depends on m3 and m1 depends on m2. So you choose m3 be equal to 1. If that is the case, then m2, we said you can choose m3 from the last column of the identity matrix of a 3 by 3 matrix, okay, and that if you choose 0, you have all the entries to be 0, or all the m1 m2 m3 to be 0, and you don't want that solution. You want a solution that will get a value. So if you choose m3 equals 1, you have m2 equals 250 over 559. Okay, that will be my m2, and it means that it will be equal to 0.4472 in 4dp, and then m1 will also be equal to 0.2000. okay, it means that my v1 is simply equal to 0.2, okay, 0.2, because 0.2000 is that, or you can add it so that you see that you approximated it to 4dp, and this is 0.477. Is it 447? Yeah, 447 rather. Okay, the decimal you get when you divide this by 250 over 559. Okay, 4472, and you have 1 here, where our lambda 1 is equal to was 2.236. okay, with this. So you can go ahead and solve for the remaining lambda and the rest. Okay, you can, when lambda 2 equals, I'll write the answer and ask you to do it. Okay, you know how we went through the process. You can divide through by something, and I'll write the coefficient matrix for you. A minus lambda I will give me, that the coefficient matrix will give me, is minus lambda 1 0 and the rest. So he'll get 2.23 Wherever you see lambda, you put it there in the a minus lambda equation. Okay, 2 3 6 1 0, have 0, negative 5, 2.236, then 5, 1, 3.236. So like I did, if you want to reduce this, what you have to do is just divide the first entry, 2.236, okay, divide by negative 5, and you get something. Okay, you get negative 0.4472. Okay, like that. Let me 4472. Let me do it well. 4472. Okay, then you continue like that. So as you continue, what you get will reduce this. So you do it for the same thing, and if you do it properly, you get your v2 to be equal to, I've done it here, and I want you to also go through the same process, and you get something like 0.2, okay, 0.2000, then negative 0.4772, and you get 1 here. Okay, the other one, I think it is negative 0.74772 rather. Okay, you divide, because when m3 equals 1, you know m2 will be equal to just this fraction. Okay, just only this fraction, so you divide it, and what you get, you put it there. But I believe this is right. Okay, so and then lambda 2 is equal to what? Negative 2.236. Okay, so let's do for the last one, and we'll write the general solution. Okay, so when lambda 3 is equal to 1, what is my solution? We know a minus lambda I to be equal to minus lambda 1 0 0 minus lambda 1 negative 5 5 1 minus lambda. Okay, we're saying lambda is equal to 1, so it means we have minus 1 1 0, okay, 0 negative 1 1, negative 5 5, negative 4, sorry, 1 minus 1, so I have 0. Okay, now if I want to reduce this is very, very simple for me to reduce. Okay, because it's very simple. Like I said, it's very, very simple. Negative 1 1 0, okay, 0 negative 1 1, negative 5 5 0 as well. Okay, so if you want to reduce this is very simple. Just negative 1 over negative 5, and that is 1 over 5. Okay, so first of all, row 3 is equal to row 1 minus, since we had positive here, minus 1 over 5 row 3. Okay, and this will reduce row 3 to, since here is already 0, that is why we are only reducing that part. Negative 1 1 0, okay, 0 negative 1 1, then 0. Okay, and here too we get 0 as well, this minus 1. Okay, yeah, so here too will be 0 as well. Okay, now since we have this, we just multiply by v3, and then let's call v3 to be t1 t2 t3, and we say this should be equal to 0 0 0. Actually, in fact, this matrix is the a minus lambda I. Okay, and that we say it multiplied to v3 should be equal to 0. Okay, so from here we can generate equations from here. Okay, we can say that for second row we have t2 minus t2 plus t3 should be equal to 0, and we have t1 minus t2 equal to 0. It means t2 is equal to t3 from the first equation, and t1 is equal to t2. Okay, now with this, if I choose t1 or t3 is equal to 1, it's row vanity, so we have to choose for t3 is the how do I put it, it is free variable, like that's how you call it. Okay, it's free variable. Okay, so with this, it means t2 is equal to 1 and t1 is equal to 1. It means that my v3 is equal to 1 1 1 with lambda 3 equals 1. Okay, so it means the general solution for this, since we have distinct roots and eigenvectors, we have y of t, x of t, z of t should be equal to c1 v1 e to the lambda 1 t plus c2 v2 e to the lambda 2 t plus c3 v3 e to the lambda 3 t. So the solution would then be equal to c1, then my v1 is what? So you go to your v1, which is equal to 0. Okay, 0.2000 and 0.47721, then e to the lambda 1 is what? 2.236 t plus, okay, like this. Then go to c2, then 0.2000 negative 0.4771 e to the negative 2.236 t. Okay, so we go ahead and let me push this down here. Okay, and push it down here, plus c3 111 e to the 1t. Okay, so that is it. This is a general solution to what we had. So the eigenvalues are 2.236, negative 2.236, and here there's a 1 here, so 1, and the eigenvectors are these. Okay, I hope you are okay with this. So thank you, and don't forget to subscribe to my channel. Okay.